Now, how do you analyze a sinusoidal wave? Let's look at it first. See, the figure shows a sinusoidal wave. As you can see here, this is amplitude and this is the time period, and here the time is given in seconds and here it is the in radians. So, this function, this series can be defined in terms of A0 plus C1 cos omega 0 t plus theta. Okay. Now, the next waveform, say for example, after stress the strain follows, there could be a lead or a lag. Say in the case of a stress and a strain, so this cos omega 0 t, this defines the first series, then the next series here will be lagging behind. Say for example, this is a strain response, so it will become cos omega 0 t minus pi by 2. Likewise, you can have a leading response. Say for example, this is the original wave, then this wave actually leads. Okay. So, how you decompose this wave? So, as I said, your wave can be, a sinusoidal wave can be explained like this as A0 plus C1 cos omega 0 t plus theta. Now, I'll just decompose this cos A plus B as cos A cos B minus sin A sin B here. So, you can rearrange this expression as Ft is equal to A0 plus A1 cos omega 0 t plus B1 sin omega 0 t, where A1 is your C1 cos theta, here C1 cos theta, and B1 is your minus C1 sin theta. So, this representation of the series will actually help you in identifying what is the in-phase component of the series and what is the out-of-phase component, which will be helpful for you in determining the dynamic modulus and the phase lag. So, or a sinusoidal wave actually in this form. Okay. So, this is, you can see how the decomposition is done. So, this was your original wave which is shifted by a distance of A0 as here. So, this A0 forms the first wave and this is the A1 cos omega 0 t, which is your in phase wave, and this is B1 sin omega t, this represents the out of phase component. So, this waveform, as you see here in this first figure, is like now decomposed into three forms as shown here. Okay. Now, in your test, in your dynamic modulus test, these are some of the typical outputs that you get. So, this is first one is the axial stress versus time. So, here is the 0, I have just plotted it a little higher. So, these are some 10 cycles I have randomly picked from the test data. So, you see the axial stress on the y-axis and the time, and you see that this is a Haversine loading that is applied. Okay. Now, as I said, you use 3 LVDTs for the capturing of strain response. Okay. These are shown. The response from the strain LVDTs or the LVDTs are shown here in these 3 colors. These are the 3 LVDTs. Okay. As you see that the response is also Haversine in nature, but it is not horizontal. Why? Because as you know that in every test cycle, there is going to be a recoverable deformation as well as an irrecoverable deformation. Okay. So, if I see this, this is the first strain response. So, if I go, okay, as you go further and further, you see that there is certain amount of deformation, this is irrecoverable. Okay. So, if it is strain, this is irrecoverable strain. But what we are interested in this computation is only the recoverable strain. Okay. What is recoverable? So, the peak to peak strain is only what we are interested in, but one should understand that there is always that irrecoverable deformation and your strain is going to shift like this. Okay. So, and also one should understand from this figure is that all the 3 LVDTs need not give you exactly same value. As I said, this is a highly heterogeneous material. So, you see variabilities in data in the 3 LVDTs. Normally, what we do is that you average out the data from all the 3 LVDTs. Now, how to process this data? As I said, your loading wave is going to be something like this. Okay. So, this is a Haversine load pulse. So, this is with time. This is your stress pulse. Now, whatever definitions that we have given for dynamic modulus and phase lag is in terms of a sinusoidal wave. So, I just have to center this data so that it will look like a sinusoidal wave. So what is done is that you take all the data that is collected for stress. Say for example, I have in one stress cycle I have collected 50 data points. Likewise, for all the data, whatever stress data you have collected, you average it out. So this is sigma I by n, sum of sigma I by n will give you the average stress value. Then what you do is that from every data point you subtract that average stress value. Okay. So what happens is that your data becomes something like this. Okay. So this is what essentially we do with the data. What you have done is that you have simply shifted the origin to a little higher. Okay. So that the response remains the same, but you can represent it in the form of a sine wave. Now, this temporal variation of the stress data that you have collected with time and the stress, this you can fit a regression equation for this, so that the Fourier series, it will look like the Fourier series as we have already explained. So, your stress wave can be represented as A sigma 0 and A sigma 1 t, A sigma 2 cos omega t and A sigma 3 sin omega t. Okay. So, I have 4 different coefficients and the stress these coefficients can be collected using any curve fitting algorithm. You have to understand that there is no model used in here, it is just a fitting of that curve with a series like this. Okay. Now, of this, A sigma 0 is the first coefficient which will represent the stress offset coefficient, as we have seen when we try to decompose this stress wave. Okay. And the second one is A sigma 1. This is the one which corresponds to the linear drift of stress. Say for example, if there is any drift in the stress data, but normally we apply the data for the 10 cycles, we see that it's mostly constant. So this term essentially goes to 0, but since we want to have a similar expression for this strain as well, so it is kept there as such. And the third term, A sigma 2, this corresponds to the stress in phase coefficient, as I already mentioned. And the fourth parameter, that is A sigma 3, that corresponds to the out of phase coefficient. Okay. And omega is the angular frequency in radians per second. T is the time and sigma is the centered data that we have collected. Similarly, for the LVDT data, that is the strain data also, you can fit a equation like this, whereas for each LVDT data we will fit a model. So, say for example, epsilon I, where I corresponds to the LVDT. So, you have I is equal to 1, 2 and 3 for the 3 LVDTs. Okay. Again, these are the parameters: A epsilon 0 for the ith one, A epsilon 1, then A epsilon 2 and A epsilon 3 are the parameters. In a similar way, A epsilon 0 corresponds to the offset coefficient, A epsilon 1 is the drift of strain. Okay. As I said, you have a drift in the strain data. And next is A epsilon 2 is the in phase component and A epsilon 3 is the out of phase component. Okay. And the other terms remains the same. Now, from this data, you know what is the in phase coefficient and the stress out of phase coefficient. As root of square of in phase coefficient plus the square of out phase coefficient will give you the peak to peak stress value of the data. Okay. Similarly, for the strain, you can get the peak to peak strain from the in phase coefficient and out of phase coefficient, squaring and adding and taking the root. And as I said, you have 3 LVDTs, so you will get 3 epsilon 0 values or the peak to peak strain values from the 3 LVDTs. You can take an average of the 3 values to find out how much is the peak to peak strain value. And as we have already discussed, mode of the modulus or the mode of the E star will be given as sigma 0 by epsilon 0. So, this gives you the dynamic modulus for one particular frequency and one particular temperature of testing. Now, coming to the phase angle, see from this equation, you have the in phase and the out of phase component for stress. You can take a arctan of the out of phase component by the in phase component, that will give you the phase lag for stress. Similarly, the phase lag for strain for the ith LVDT can be taken from the in phase and the out of phase components as arctan. And for all the 3 LVDTs, you take an average to find what is the phase lag in strain. So once we get the phase lag in stress and the phase angle in strain, you can take a difference to find what is the phase lag between the stress and the strain in terms of omega. Now, this is a sample data from a test that is conducted at IITM on a specimen at 6 different temperatures, and we have done it for 10 different frequencies starting from 25 Hz to 0.01 Hz. Okay. So, here dynamic modulus is in the y-axis in megapascals and frequency is in the x-axis in Hz, and each line represents one temperature. Okay. So, let us see the 5 degree Celsius data. So, this black line is your 5 degree Celsius data. You see that as the frequency increases, you know that the dynamic modulus increases. As I said, higher frequency, shorter duration of load application, and higher will be the modulus response. The material will be behaving more like an elastic material. So, your modulus will be very high. As we go down to higher temperature, say this is 15 degrees Celsius, this is 25, this is 35 and so on. So, as we go to the higher and higher temperatures, you see that the modulus value has decreased, which is quite obvious. And in all these cases, so you can see here, this is the last one is for a temperature of 55 degrees Celsius. You start with a 0.01 frequency, and then as you go to higher frequency, it has slightly increased. Okay. Now, let us look at the phase angle data. So, here you have the phase angle in degrees, and this is the frequency in Hertz provided for all the different temperatures. Say for example, this is the 5 degree data, the black color one is the 5 degree data. As expected, as your frequency increases, the material behaves more like a elastic material, so the phase angle is going to decrease. Okay. At 5 degrees Celsius, as the frequency increases, here as the frequency increases, you see that the phase angle is actually decreasing. Similar is the case with 15 degrees Celsius, 25 degrees Celsius and as well as 35 degrees Celsius. Okay. Between the temperatures, as we know that if the temperature keeps on increasing, your more and more viscous behavior will come into play and your phase angle will be more. So, as you can see from here, the bottom line starts with 5 degrees Celsius and the phase angle is actually going up when your temperature is increasing. But what is interesting here is that at 45 degree and 55 degrees Celsius, the variation of phase angle with frequency is not following the trend as we have discussed so far. So, this is something which the material response is all about. So, this is a complicated behavior. So, at higher temperatures, though we do the test at a lower strain levels of say 75 and 125 microstrains and expects that the material is in the linear viscoelastic regime, it shows such behavior as well. So, one has to be very careful in interpreting the data. Okay. Now, so this is how we estimate the dynamic modulus of the material and phase angle of the material in the laboratory. In MEPDG, they also suggest that if this testing setup is not available, you can go for a predictive equation. So, they have provided a predictive equation to find out E star value. This is actually mode E star value or the dynamic modulus value. So, this is dynamic modulus, though it is written without that mode in lines. Okay. So, this you can see that it is a function of various parameters like of course the loading frequency, then air void content of the sample, then the bitumen viscosity and the effective bitumen content and the various aggregate parameters or the mixture parameters. Say for example, the percentage of material retained in various sieve sizes, or it is essentially the gradation of the mix. So, in terms of all these parameters, this dynamic modulus predictive equation is given by MEPDG. So, one can also use this predictive equation. So, how does one uses this dynamic modulus and phase lag data in the mechanistic empirical method of analysis? As I said, you can do this test at various temperatures. Say in the example that I have shown, we have done it for 6 different temperatures and at different frequencies. Okay. But in the analysis, one may encounter other load frequencies as well as other temperatures. So, in order to get that particular value, what you normally do is that you prepare what is called as a master curve. So, you shift this data into a sigmoidal function to represent one general expression or one general curve which will give you the dynamic modulus and phase lag for any particular temperature or frequency that you are looking at. Okay. So, the preparation of dynamic modulus master curve is explained by Professor Padma in her lecture. So, we actually use a constrained fitting method so that your data is fitted to one sigmoidal master curve. Okay. So, as you can see here, this is taken from MEPDG. So, they have taken a reference temperature of 70 degrees Fahrenheit, which is approximately 21 degrees Celsius, and the data that is collected from different temperatures, say minus 16, 40, 70 and 100 degree Fahrenheit, they are actually shifted like this to form one sigmoidal curve, and this forms a reduced frequency which is used to shift the data, and the various shift factors which are adopted for each of these temperatures is provided here. Okay. So, one can prepare a master curve, and it is this master curve which goes into the MEPDG analysis, so that for any loading or any loading frequency or any temperature that is encountered in the analysis, the corresponding dynamic modulus value can be taken from this master curve. Okay. So, this is how MEPDG suggests this methodology works, is that, see, you have to develop a master curve and the shift factors for the reference temperature of 70 Fahrenheit as they have suggested. And another important aspect that is considered in MEPDG analysis is that the aging of the material can also be included in this analysis. As we know, as the service life increases, the material will start aging, okay, due to many reasons. As I said, this is already discussed by Professor Nivita in her lecture. Okay. So, when the material ages, the modulus also will change. Okay. So, the effect on the payment will be different if it is an aged material. So, this also can be incorporated in the mechanistic empirical analysis. So, they use it using a global aging model, so which is also incorporated. So, using those models, you calculate the appropriate viscosity change in the material if it is aged, and then that viscosity will be used to calculate the dynamic modulus. So, two things are here. One is that the dynamic modulus that is captured and the master curve that is prepared which goes in, and over a period of time what happens to this dynamic modulus will also is also incorporated in the form of the temperature or global aging model. Okay. So, when you do an analysis say for over say 20 years or 15 years of time, so at every instant of time, according to the kind of loading and according to the temperature at that instant, the modulus will be taken from the dynamic modulus master curve, and as the age passes, you have to incorporate the effect of aging also, and the modulus value has to be appropriately corrected. Okay. So, this is a whole process that is being done in MEPDG. So, I will summarize. So, in MEPDG, so this is a general framework of how MEPDG analysis works. So, there is a traffic model, you give the input data which is the environmental effect and the distress, okay, environmental effect, and you do the material characterization. So, these material characterization models will go in as a response, go into the analysis procedure where the primary response model will compute what is the stresses, strains and the deformations that happens, and then they are connected to the distress model. As I said, this is the response of the material in the laboratory. Now, this has to be correlated to what happens in the field. So, the stresses and strains developed are actually correlated to the field rutting and fatigue behavior in the form of distress transfer functions, and in the distress transfer function you will check whether the payment will sustain the type of loading without any failure in the form of rutting or in the form of fatigue cracking, and if it is satisfactory you will proceed with the different layer thicknesses and the materials that you have used, otherwise you will repeat the process. Okay. So, this is the whole outline of MEPDG. Though we are not discussing this payment design in this course, I just want to emphasize emphasize the need for a modulus which is time dependent as well as temperature dependent to be used in a payment analysis strategy, so that you can design the payment according to the actual response of the material in the field. Okay. So to summarize, what we have seen is what is a dynamic modulus and what is the stress function, or how the loading is applied to test this material, and what is the data that you collect, and how do we process this data in order to arrive at the dynamic modulus value as well as the phase angle value, and also at what temperatures you have to do it and at what frequencies that you have to do it is what we have discussed. Okay, thank you.